Here in section 5.6, our primary goal is to extend the list of triangle congruence principles that we had. I call them all principles. Some are postulates. One is a postulate, the rest are theorems. We'll add two more that are theorems. They will be angle, angle, side, and hypotenuse, leg. And then that will be it for us. We'll have 5 total: side, angle, side, 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 angle, 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 side, and hypotenuse, leg. And we'll also return to the proof of the converse of the ITT. You might recall that we proved it previously. We can now prove it in a simpler fashion. So, angle, angle, side, and hypotenuse, leg. You can gather from those names what precisely they say. You're familiar with the way that we've named triangle congruence principles before. So what angle, angle, side would have to say is this: if two angles of one triangle equal two angles of another, and a pair of not-included sides which correspond are equal, then the triangles are congruent. Right? There's, of course, a reason why the S is not in between the A's in the name AAS. It's that the pair of equal sides are not in between the pair of equal angles, and of course they have to be sides that correspond to one another. So here is a nice little picture to go with that. We have two triangles ABC and RST with two pairs of equal angles, namely angle A is equal to angle R, and angle C is equal to angle T. And we also have a pair of equal sides, BC and ST, which do correspond. An easy way to see that is that in each of the triangles, the single hash side, either BC or ST, is opposite the single hash angle, either angle A or angle R. Okay, so this does fulfill the conditions for angle, angle, side, and it follows, I say, that in this case the triangles are congruent. That is, triangle ABC is congruent to triangle RST. As for how one proves this, it's really a simple matter. It's one of the simplest proofs that I ever ask you to do. Think back to the third angle theorem corollary of the triangle angle sum theorem. We have two angles of triangle ABC equal to two angles of triangle RST. What follows about the third pair of angles? Well, it follows, of course, that angle B is equal to angle S. And once we've said that, then the triangles are congruent by angle, side, angle. So the third angle theorem, or third angle corollary, transforms angle, angle, side immediately into angle, side, angle. So there we go. Angle, angle, side works. Now let's talk about hypotenuse, leg. It's not particularly hard, but it's a little bit harder. And it says this, okay? If two right triangles, which of course is indicated by our talk of hypotenuse and leg, if two right triangles have equal hypotenuses and a pair of equal legs, then those triangles are congruent. So here's our picture. So we have right triangles ABC and DEF with the right angles at C and F respectively. We have their hypotenuses equal. That is, AB is equal to DE. We also have a pair of equal legs, namely BC is equal to EF, and it follows, I say, that the triangles are congruent to one another. As for how one does this, well, it begins with the construction. So let us take triangle ABC. We could also do DEF if we wanted, but we'll take ABC. And let us extend AC through C out to a point Z, so that CZ is equal to DF. And these are all allowed constructions. They're all familiar constructions. And then finally, let us connect Z to B. That is, construct segment ZB. And let's think about the relationships that we have. I'll put this as a series of questions, okay? So let's first of all consider angle ZBC, okay, which for convenience I will call simply angle 1, perhaps. Let us consider angle ZBC. ZCB. Well, the perpendicular lines theorem is still true. So, of course, angle 1 must be a right angle. So let me draw that conclusion in. And now consider the relationship between triangle ZBC, that constructed triangle, and triangle DEF. I have two sides of one equal to two sides of the other, and I have concluded angles equal as well. So it follows that triangle ZBC is congruent to triangle DEF, of course, by side angle side congruence. So let me just sort of bullet point the high points, or just like number the high points of the proof. Okay. So let's see. So like 1. Okay. So angle 1 is right. Okay, you can provide the reasons for this when you actually write the proof out. And then it follows that triangle ZBC, hopefully you still take care with the order of the letters in these, is congruent to triangle, I believe it should be DEF, and that will be by side angle side congruence. And then it follows that BZ is equal to DE, and that of course follows by CPCDE. So let us put helpful hash marks in. So this now follows. And then at this point, consider triangle ZBA, okay? And of course, it must actually be a triangle. The path from Z to C to A is a straight path, just by construction, so ZBA is really a triangle. It is isosceles, okay? ZB is equal to BA. So it follows by the isosceles triangle theorem, I'll call these 3 and 4, that angle 3 is equal to angle 4. Okay? And now consider the relationship between triangle ZBC and ABC. Notice that we, at this point, have 2 angles of one equal to 2 angles of the other. Angle 3 is equal to angle 4, and the right angles are equal. And we also have a pair of equal sides that correspond. That could be just CB. So we could say that triangle ZBC is congruent to triangle ABC. And then look at lines 2 and 5 together. We know that ZBC is congruent to DEF, and we know that ZBC is congruent to ABC. And we know that the congruence relation is transitive, so of course it follows that DEF is congruent to ABC, which is what we were supposed to prove. And with that, the proof is complete. All right, just a quick note about terminology here. If you look back, and I'll pop back to the original diagram. If you look back to the diagram, and I've had students say this multiple times, they'll say to me, Dr. Mason, isn't this just angle side side? And yes, ASS does appropriately describe this, right? When you look at the diagram, we have a pair of equal angles, F and C, and then as we go around the triangles, we have CB equal to FE, and then we have a second pair of equal sides as we continue our way around. BA is equal to ED. So yeah, ASS is a correct description of the equalities of angles and sides, but yet I request that you not call this ASS, okay? Because we know that there are counterexamples to angle side side, okay? So angle side side, what this means is that angle side side sometimes works and sometimes does not work. One case in which it does work is the case in which the angle is a right angle. Okay, so let's not use that general name, angle side side, which does have counterexamples, but let's use the specific name for the case of angle side side where the angle is right, and that's hypotenuse length. Okay, so this is not permission to begin to use ASS in your proofs. Don't do that. That would suggest to me that you think that ASS always works. It doesn't. Use HL. Okay. Now, finally, let's look at the converse of the ITT. This was proven previously. I don't know if you recall, but I had you prove it in a problem set. I had you recreate Euclid's proof of this. It was indirect. There is now a much more direct proof of this that models, or mirrors, I should say, the proof that we had of the ITT itself, which is something that we would like to have. So here we go. We have triangle ABC with angle A is equal to angle C, and we wish to prove that AB is equal to BC. This is precisely the converse of the ITT. And you might recall that in our first proof, anyway, of the ITT, we did this by the introduction of an angle bisector. We can now do the same here. So let us introduce the angle bisector. The angle bisector will be the angle bisector of B, and this will go down to a point, let us call it D on AC, and then consider the 2 triangles that result. I apologize for the poor quality of the diagram. These are now congruent by angle side, right? Because BD, of course, is a shared side. And then once we've said that ABD is congruent to CBD by angle side, of course, it follows that AB is equal to BC by CPCTE. And this is very nice. Okay, so we have a proof now of the converse of the ITT, which very much mirrors, or very much is like the proof that we had originally of ITT. To prove the ITT, we bisected an angle and then use side angle side. To prove converse ITT, we bisect an angle and then use angle side.